Hello, this is Jude Socrates, and welcome to A Portrait of Linear Algebra. Our video for today is called Diagonalization, and I think this is the first time that we have a title which is just one word. So we are going to find out today what is the meaning of this concept of diagonalization. How can we decide if a matrix is diagonalizable or not? So spoiler alert, there will be some matrices which are diagonalizable, and there are some which are not. So for those which are diagonalizable, we will perform the diagonalization algorithm. So here is our main definition. Suppose you have an n by n matrix A. We will say that A is diagonalizable if we can find an invertible matrix C such that C inverse times A times C is another matrix D, which is a diagonal matrix. So D can be written as diagonal alpha 1, alpha 2 through alpha n. So these are the entries on the main diagonal of your matrix D. There are two equivalent ways to write out the equation in this definition. So we can move C inverse to the right by multiplying both sides of this matrix by C. So when it moves to the right, it becomes C times B. And on the left, we have left behind A times C. Now we can go one more step. We can move the C on the left to the right by multiplying both sides of that equation by C inverse. But this time, C inverse will appear on the right side of D. We will say that this matrix C diagonalizes A, and this matrix product, C inverse AC, it appears a lot in mathematics, and that is called conjugating the matrix A by the matrix C. If a matrix is not diagonalizable, we call it a defective matrix. So from the sound of it, it looks like being diagonalizable is a desirable characteristic. We don't like being defective, right? Okay, so how are we going to go about deciding if we can diagonalize a matrix A? So the key here is to focus on the second equation. A times C is C times B. Just keep in mind that C has to be an invertible matrix. All right, so first step, look at that equation. Next step, break down C into its columns, like what we've done before. So suppose you have V1, V2, 3 through Vn as the columns of C. All right, so we already know what A times C looks like, okay? When we defined a matrix product, we said that's just AV1, AV2 through AVn, okay? So what we don't know, not exactly, is what does C times B look like? Okay, what does this matrix product look like? Okay, so here's the demonstration. I have a random matrix C here on the left, and I have a diagonal matrix D here on the right. Okay, so remember those alpha 1, alpha 2, alpha 3. In this case, they're just -4, 3, and -7. What happens when we multiply these two matrices together? Okay. What is the relationship now? Can we see what that relationship is? I believe, look at column 1 and look at column 1 in the original matrix. It looks like everything here got multiplied by -4 to produce the new column 1. Okay, what about the third column? That entry is -7, so -35 plus 63 -7. Yes, multiply each column by the corresponding entry in the diagonal matrix. All right, so now we're ready to understand both sides of the equation. A times C equals C times B. All right, so we said that the left side is just A times column 1, A times column 2, and so on. But the right side is now multiply column 1 by alpha 1, the first entry on the diagonal, and so on. Multiply column 2 by alpha 2. So what has to happen? This is the first column in the product. It has to be equal to the first column on the right. Okay, so AV1 has to be the same as alpha 1 V1. Doesn't that sound like something we have been looking at in the last two videos? Yes, it's an eigenvalue eigenvector equation. Okay, so of course it has to happen for every column. So A times each column VI has to be the same as VI times the corresponding alpha I on the diagonal. Okay, so what does that mean? These vectors have to be eigenvectors, and the alpha i's have to be eigenvalues. Okay, so that gives us the basis test for diagonalizability. Why basis? We said that C has to be an invertible matrix. So therefore, the columns of C have to be linearly independent. Okay, remember that's one of the conditions in the really big theorem. So therefore, we have n vectors from Rn, which are linearly independent. Okay, 2-for-1 theorem, that means that they have to be a basis for Rn. All right, so that's why this is called the basis test for diagonalizability. Let A be an n by n matrix, then A is diagonalizable if and only if we can find a basis for Rn consisting of n linearly independent eigenvectors for A. Let's call them V1 through Vn. If this is the case, then the diagonalizing matrix C is the matrix whose columns are V1 through Vn. And the diagonal matrix B contains the corresponding eigenvalues along the main diagonal. So I hope you remember, since the first video in this sequence on eigen theory, that I was asking you to get into the habit of listing the eigenvalues in increasing order. Okay, we are going to diagonalize a few matrices now. And in your homework, of course, you're going to do the same thing. So if you want your answer to match the answer in the answer key, then you need to list the eigenvalues in increasing order, okay? Because that is how I perform the algorithm. Okay, so let's look at our first example from section 8.1. We did this 2x2 matrix. It was very easy to get the eigenvalues and get the eigenvectors. Okay, so every eigenspace was just one-dimensional. Our eigenvalues were -4 and 7. Now, I wrote down the two equations that appear in the definition because, even I was a little bit confused about them in the beginning. On the left, you have C inverse AC has to be the diagonal matrix, but CBC inverse must be the original matrix A, right? So notice that C inverse is on the left in this equation, but it's on the right here. Did I say confusing? Yeah, it's a little bit confusing, right? Okay, so let's perform the algorithm. Okay, so the theorem said that we need to have a basis for R2 made of eigenvectors. Well, we have two candidates over here. You have two vectors from R2. They have to either span R2 or be independent. And again, independence is always the easier property to check. Independence in this case means, are they not parallel? Okay, remember that a set of two vectors is independent if and only if the vectors are not parallel to each other. And yet, they're clearly not parallel. The only way to get 2 there is to multiply this vector by 2. We should get 6 instead of 5. So, yep, they are not parallel. So we can go ahead and put our invertible matrix. and it's 2 by 2. So again, you want increasing eigenvalues. So we will put 5, 2 in the first column and 3, 1 in the second column. Okay, so we need C inverse in both of these equations. Okay, so compute matrices inverse. Okay, so this is a little unusual, right? The inverse does not have any fractions. And why is that? 5 times 1 minus 3 times 2, 5 minus 6, negative 1. Aha. So still integers. Okay, so let's see, we have C. Now how about D? Okay, well, I could create the matrix D, but I can also have Maple do it for us. Okay, so let's label this. This is C inverse. It does say inverse there. Okay, check out this equation. If I have C inverse first on the left, okay, and then I put A on its right, and then I put C to its right. If I did this correctly, I should come up with a diagonal matrix. There it is. Okay, so it does contain negative 4 and 7 on the main diagonal. Okay, just for fun. Okay, how about this equation? So this equation is also amazing by itself because it tells us that A can be factored into 3 matrices. A matrix on the left, C, which happens to be invertible. Its inverse on the right of this sandwich. And in the middle, you have a diagonal matrix. Okay, so let's go ahead and check. If you put C on the left, which is over here, and then you put the diagonal matrix in the middle, containing the eigenvalues, and we put the inverse now on the right. Okay, so once again, they change positions, they switch. Okay, we should get 8. And yep, of course we do. That's our original matrix. All right, for our second example in section 8.1, we had a triangular matrix, an upper triangular matrix, and we had 2 eigenvalues. So in this case, we can see them right away. Negative 2 and 7 are the eigenvalues. So for negative 2, it was a 1-dimensional eigenspace. But for 7, it's a 2-dimensional eigenspace. Okay, so this is a little very different now. Well, we have a 3 by 3. But also we have lambda minus 7 squared in the characteristic polynomial. In our next video, we are going to investigate this a little bit further. Okay, it's not an accident that lambda minus 7 is squared and you have a 2-dimensional subspace here. Is it always going to happen though? We'll find out. Okay, so the algorithm said put together in C 3 eigenvectors. And we have 3 eigenvectors, except this time. Is it obvious that if we put the 3 of them together, then you get a linearly independent set? Okay? Well, in this case, we can still say that it is. These 2 vectors are obviously not parallel to each other. Okay? What do 2 non-parallel vectors span in R3? We get a plane. Okay? Is this vector on the plane? Okay? No, because the plane happens to be the eigenspace for lambda equals 7. Okay? But the eigenvalue for this subspace is negative 2. Okay? So therefore, this vector cannot be on this plane. Okay, so let's put together our matrix and confirm that we do get an invertible matrix. So -2 is first. We have -5, 3, 0 in column 1. Now for 7, we can actually put them in any order that we want, okay, within each eigenspace. But, why not do it in the natural order? The order that we got our basis by sight reading the null space when we got what? A minus 7, I3. Okay? So, is that matrix invertible? Compute matrices inverse. Yep, that is an invertible matrix. Okay, so, I did not put down the two equations. Okay, so this is how I remember it. Remember that we tested D multiplied to the right of C. Okay, so it's AC equals CD. Okay, so actually that is another way to test if your matrix is correct. Okay, is AC equal to CD? Okay, so here is our A, and then we multiply to C, and we get this matrix. Okay, so yeah, we have eigenvalues -2, so we will get 10 minus 6, and 7. So we get 7, 0, 0 over here, and 0, 14, 21 in the third column. Okay, how about C times D? Okay, oh, we don't have a diagonal matrix, so let's make one. 3. So our diagonal matrix is -2, 7, 7. Okay, so these are zeros, 0, 0, 0, 0, and 7. Oh, okay. So now we need C to the left. Okay, so C times D, and we get, yep, exactly the same matrix as A times C. Okay, so now let's do the factorization. Okay, so if I want A, I need to move C to the right as C inverse. All right, so we want C times D times C inverse. I already have C times D over here. So I'm just going to recycle now that we know they're the same. We need C inverse to the right. Okay, so when we multiply them together, I still have A over here. Excellent. So we should get A when we multiply those three matrices together. And of course, yes, we do. Okay, so remember that when we saw the first video, we messed around with some of the entries in the upper part of this triangular matrix. Okay, what would happen if we change the 15? Okay, let's make that 14. Okay, so luckily we have a computer. Compute matrices, eigenvectors. Ooh, check it out. Okay, so we still have the same eigenvalues, of course. We didn't change the -2 and the 7. But the eigenspace for 7 is now only one dimensional. Remember, we had a second vector for that subspace. So in this case, this matrix is not diagonalizable. Okay, so it is what we call a defective matrix. Okay, so let's go to our second video, and we saw this matrix, and this gave us quite a bit of grief. First, we have to find the polynomial. It's not so obvious now. And then we have to find the eigenvalues. Remember, we tried synthetic division. So we got the two eigenvalues, and we found a basis for each of those eigenspaces. So again, that's a two-dimensional subspace of R3. It's a plane. This vector is from a different eigenspace, so therefore it's not on that plane. So those three vectors, if we put them together, should still be linearly independent. So let's confirm 3 by 3 matrix. And yeah, you know what? Let me save one because we're going to make a diagonal matrix. So C will be -3, 1, 0, 1, 0, 1. And then for 5, we have -3, 1, 1. Yeah, these two columns are almost parallel, but not quite. Okay? Are you invertible? Compute matrices. Inverse. Ooh. We've been lucky. This is the second matrix that we got whose inverse is also all integers. Imagine that. Okay, so let's make our diagonal and matrix. So on D, we will have -3 twice because we have the two-dimensional subspace, and 5. Okay, so I have to fill in these entries or Maple will freak out. All right, so that is C. We have C inverse and we have D. Okay, let's do the factorization. Okay, so we said A has to be C inverse. All right, so here's C, and then we multiply D, and then to C inverse. Okay, and is that the matrix that we had in the beginning? Yeah, there it is, and it's exactly the same matrix. Okay, I saved the best for last. My favorite matrices. We have the projections onto L and onto pi, where L is the line span of 2 minus 6, 5, and pi is the plane orthogonal to that line. 2x minus 6y plus 5 is 0. Okay, so we said that the eigenvectors for these three matrices are all the same, essentially. Okay, you're either on the plane pi or you're on the line L. Okay, if your vector is already on pi and you project on the line, you'll get the 0 vector. It has no shadow on the line. But its projection on pi is itself. Okay, it was that if you put a pen on the plane, my phone, then its projection will be itself. Its reflection will also be itself. Okay, now that is a little bit of a worry because now the eigenvalues are different. Okay, so for L, when we projected on L and you're on the plane, you get a 0 vector. So the eigenvalue there is 0, but for the projection on pi, you get the same vector. So the eigenvalue there is 1. Okay, so here's what we're going to do. Okay, we're going to ignore the tradition, the convention, that the eigenvalues have to be in increasing order. Okay, because oh yeah, for reflection, we also have -1 as an eigenvalue. If your vector is already on the line, the normal line, then you reflect it across, you get the negative of that vector. Okay, so we have eigenvalues and eigenvectors all over the place. Okay, let's just make one matrix. Okay, and this is going to be amazing. So we said that the eigenvectors are on the plane or on the line. Okay, so let's put it over here. Let's put our C over here. So we said, and again, let me save. Wait, no. I just need one. All right, so let's just put that single vector in column. It's an eigenvector. Okay, whether the eigenvalue is 1 or 0, doesn't matter. Okay, now I need a basis for display. So remember we said that, if you just make one of the coordinates 0, you can eyeball the other two. So if we make z 0, x can be 3, so 3 times 2 will be 6. I want a minus 6, so y can be 1. 6 minus 6 plus 0, you get 0. Okay, what about another vector? How about we make y 0? Okay, that looks simple enough, right? So if I make x 5, I get 10. I want minus 10, so I need a minus 2. Okay? So this is obviously a basis, these three vectors, because those two are not parallel, and the third vector is not in the plane. Okay? So that is invertible. Compute matrices inverse. Yay! Okay, ooh, 65, huh? Where have we seen 65 before? Okay, so here's what we're gonna do, right? So we said that AC equals CD. I always go back to that one. If I, this time, if I want to get D by itself, I need to move C to the left. So we have C inverse AC, all right? So I will put C inverse to the left of these three matrices. 1, 2, and 3. Okay, so that's C inverse on all of them. Okay, and then I will put C on the right. So C is here, 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 and here. Okay, so this is going to be amazing. All right, what happens when you multiply these three together? Boom. Ooh. So we have eigenvalues of 1 and 0. Okay, so if your vector is on the plane and you project onto L, you get 0 vector. Yeah, so these two columns turn into zeros. What about projection on pi? So this time, I'll give you a little time to think about it. This time, who turns into 0? Ready? Ooh, okay, so this time, if you're on the line, you turn into the 0 vector. If you're on the plane, you stay the same vector. Okay, last example. Okay, so now we're reflecting across pi. Okay, yeah, you remember what happens if you're on the line and if you're on the plane. What happens to you? Aha, there you go. So the eigenvalues are -1 if you're on the line and +1 if you're on the plane. Okay, so that is our video for today. I hope you enjoyed it. This is also one of my favorite topics, and it has so many uses, especially in this modern age of data mining and data analysis. Eigentheory is everywhere. Okay, so for those of you who are taking more advanced classes, I hope you learn someday about the singular value decomposition. And I hope you remember the time when you first learned about eigenvalues and eigenvectors. So until our next video, this is Softy signing off. You'll find me on Facebook, and you'll find the 4th edition on Facebook and at candlehunt.com. So until next time, I hope you enjoy the rest of your day.